These are the values of the resistors, and I don't know if you can see it very well, but there are little bands of color going around each of the elements, and it turns out that brown, black, orange is a 10,000 ohm resistor. And this brown, black, red here turns out to be a 1 kilo ohm resistor. So I'm reading those colors from the top. This is called the color code, and you can go online and Google color code, and you'll find lots of calculators, what are called calculators for color codes. You type in the colors and they'll tell you what the resistance is, or you can type in the resistance and they'll tell you what the colors are. And you should remember them as you get deeper into electrical engineering. But the important thing here is size does not determine the resistance. What determines the size of a resistor is how much power it dissipates. And I'm showing that in the next slide, where I have a much bigger resistor. So here's that resistor, and you can see it's quite much bigger than the other resistors I had. And if you look at it very carefully, you can see it says it's 75 ohms, and I don't know if you can see it very well, but down below what I just wrote over, it says it's 25 watts. So this will dissipate lots of power. It turns out it's hollow inside, and that's there to allow more power to dissipate from this. So this is able to put out lots of power. I'm sure you've seen light bulbs. In the US there's 60-watt light bulbs, and they can get very warm very quickly. You can imagine the 25 watts can also get pretty warm. These quarter-watt resistors don't get warm at all. So let me show you a capacitor. And you can see on the left there a 470 microfarad capacitor, and it's pretty big. There it is. It's pretty good size, bigger than my finger in diameter. And that's, like I said, a pretty hefty sized resistor. On the right is a 1 nanofarad resistor, 1 nanofarad capacitor, what am I saying? A 1 nanofarad capacitor, and it's small by comparison, and you'll find that size capacitor in lots of electronic circuits. Finally, let me show you an inductor, and here's the inductor that's in that photograph. It's about finger sized, and if you look at it carefully, it is a coil of wire coiled around a circular object. And I want to point out something. If you look very carefully at this figure, you can see that the wires coming out look to be silverish. They're not really silver, but they look silverish, whereas they look to be brownish around the coil. And it turns out the brown does not indicate that they're copper. That brownish substance turns out to be an insulator, because if this wire was not insulated, right over here, for example, the wires are touching each other, and it would short out the entire inductor. Because they're insulated, this coil of wire now looks like an inductor. And you'll find this, it applies very consistently throughout electrical engineering, that when you tend to see that kind of color, it's indicating that it's a insulated wire. You can scrape it off if you want to get rid of the insulation. Also, as you know, there's a plastic kind of insulation on lots of wires too. But in this special case, I wanted to indicate that this is a very small diameter kind of insulator too. Okay, let's go back and look at the circuit elements again, because there are times when you want to write the VI relations the other way, if you will. So instead of V equals RI, you might want to write I equals 1 over R times V. Well, we call 1 over R is called the conductance. It's given the symbol G, and G is measured in Siemens, named for the German inventor of and designer of telegraph systems in the early part of the 19th century. So the symbol G is for Siemens. There are going to be lots of times when it's more convenient to think about a resistor in terms of its conductance, reciprocal ohms, Siemens, than it is in terms of its resistance. We'll find that out very soon. Now, of course, for the capacitor and the inductor, those derivative relationships turn into integral relationships. And as I said, all integrals in this course are definite integrals, and they all start at minus infinity. So, in some sense, a voltage in a capacitor has infinite memory of all the previous values of the current. All previous values of the current, no matter how they arose, going back to the beginning of the Big Bang, are summarized by the voltage. Of course, there are a lot of different current patterns that will result in the same voltage. Same thing for the inductor. It's the current that contains a memory of everything, all the voltage values that voltage that the inductor has had across it. Kind of interesting that they have this kind of infinite memory, but that's what you get when you have a derivative relationship. Turn it around, comes an integral. Okay, let's talk about some different elements, namely sources. And these provide voltage or current to a circuit that we build. So a voltage source is indicated by a circle with a plus to minus indicating the positive direction for the applied voltage V sub S, S for source. So the VI relationship, again, I'm defining my own voltage V and my own current I going in the top in a consistent way, is that the voltage is going to equal whatever the source is for all I. So what this means is that the voltage source puts no constraints at all on the current. It can supply any current that the circuit to which this voltage source is attached will want. What it does is it provides a voltage for all time, whatever V sub S is. Similar thing for a current source is that this will provide a current no matter what the voltage is. Voltage could be 0, minus 100, 10 to the minus 6, really doesn't matter. It's going to provide a given current. Now, notice the little minus sign here, and that is because on this, the way I've drawn it, I sub S is a positive current flowing that way, and we always want I, defining the VI relation, to go in the positive side of voltage. So these two currents are going the opposite way, and that's the reason for that minus sign. It's just a minor little thing. You just want to make sure you're consistent in the way you define things. But let me point out, it is very, very important that if you define voltage that way, you define current going in the positive side of voltage. Very, very important. Well, let's look at some batteries. So, batteries are a special case of a voltage source that produce constant voltages. And I've got 4 batteries in this photograph. This is a D cell, which is, as you know, pretty big. It gives you a size of scale. If you read the label very carefully, it says 1.5 volts. The little button at the top is the positive side. It doesn't, in most cases, they don't label the negative side. Once you know what's positive, the other end is negative. This is a AAA battery, and if you look very carefully right there, it says it's also 1.5 volts. So again, the size of the battery does not determine the size of the voltage it produces. What it does tell you is how long each battery will provide that voltage. Basically, the bigger the battery, the more oomph, as I like to think about it, the more oomph it possesses, it can last longer. The chemical reactions can be sustained. So a AAA battery in general in a circuit won't last as long as a D-sized battery attached to the same circuit. Wanted to point out, I discovered this the other day. This is a battery that goes into my remote control for my door lock on my car. And if you look at it very carefully, right there it says 12 volts. So this actually provides a bigger voltage than a AAA, than a D cell, but it doesn't provide much current. By the way, the 27A that you may see at the top of this battery is a model number. It does not mean it provides 27 amps. I guarantee you it doesn't. And finally, this rectangular battery you see is clearly labeled 9 volts, and on the side you can look to see which end is positive and which end is negative. That's labeled on the side of the battery. Okay, you can buy these clearly at any store, readily available. So don't forget that when you buy a battery like this, it's open circuited. There's nothing attached to between the top and the bottom. There's nothing there. So if we're here, the way they're pictured, the current is 0 because there's nothing attached to it. These batteries are quite happy to produce 1.5 volts for these two at least, no matter what, because they're just sitting there. Now, how about a current source? Well, a current source will provide a current no matter what voltage is across it. Providing a current means there's flow of charged particles going out of this device. If it's open circuited, where are these charged particles, electrons, going? Where do they go? If it's really open, the current source has a real problem. It has no place for the current to go. Remember, an open circuit does not allow any current, so it's inconsistent. So it's very hard to go to a store and buy yourself a current source that's sitting there like this. It would be perfectly happy if the